That old bicycle wheel leaning against your shed wall, the one with the flat tire and the rust on the spokes, you keep meaning to throw it out. Stop. That wheel can outcut, outgrind, and outsharpen a power tool that costs $300. I didn't believe it either. I set out to prove it was nonsense, and the wheel proved me wrong on my own bench. There's a Japanese method behind it. One-blade smiths used before electricity existed, and by the end of this, you'll understand exactly why a spinning circle of scrap beats the machine you paid real money for. And it works on the wheel you already have. Let me back up, because the first time I heard this claim, I laughed at it. A buddy of mine, an old apple farmer up north, told me his sharpest blades in 40 years of orchard work were never touched by a powered grinder. He sharpened them on a wheel he built from a junk bicycle. I nodded politely and thought he was just being stubborn the way old-timers get. Then, one afternoon, my brand-new bench grinder, the $80 one with the fancy blue housing, burned the edge right off my best chisel, blued it, ruined the temper in about 4 seconds. And I stood there holding a dead chisel thinking about that old man and his stupid bicycle wheel, so I built one. I took a 26-inch wheel off a bike that was headed for the dump, and I spent one Saturday turning it into a sharpening station. The first time I ran a blade against it, I felt something I had never felt on any powered tool. The edge came off keener than anything my grinder ever gave me, and the steel stayed cool enough to hold in my bare hand the entire time. That was the moment the mystery started, because it made no sense. A cheap wheel with no motor, no name brand, no price tag, was doing something my expensive machine physically could not do, and I had to know why. Here's the first clue, and it's the one almost everybody gets backwards. When you think of a grinder being powerful, you think of speed. More RPM, more power, more cutting. That's what the marketing sells you. My bench grinder spins at 3,400 revolutions per minute, and the box bragged about that number like it mattered most. But raw speed is exactly what killed my chisel. At 3,400 RPM, a small grinding wheel throws so much friction into a thin edge that the steel heats past 450 degrees Fahrenheit in seconds. That's the temperature where hardened tool steel starts losing its temper. You see it turn straw-colored, then blue. Once it blues, that edge is soft forever. No amount of sharpening brings it back. Now look at what the bicycle wheel does differently. A 26-inch wheel is enormous compared to a grinder stone. And here's the part that took me weeks to understand. What actually matters for cutting is not how fast the center spins. It's how fast the outer edge, the rim, travels through space. Machinists call this surface speed, measured in surface feet per minute. A big wheel turning slowly can move its rim faster than a small wheel screaming at high RPM, and it does it with a fraction of the heat. My bicycle wheel, cranked by hand at just 80 revolutions per minute, moves its working surface at over 500 surface feet per minute. Gentle on the steel, brutal on the metal you're removing. That's clue number 1, and it already flips everything the tool aisle taught you. But it doesn't explain the strangest thing I noticed, which is that the wheel seemed to fight back when I pressed harder, like it was storing something. Let me stay on that, because this is where the puzzle got its hooks into me. When I leaned into that spinning wheel with a heavy blade, it didn't bog down and stall the way a cheap tool does. It pushed through. It carried the cut. It felt alive, like it had momentum I couldn't stop. And that feeling is not romance. It's physics, and it has a name. And once you understand it, you'll never look at a heavy wheel the same way again. The name is rotational inertia, and it's the secret engine hiding inside every wheel on Earth. Think about what a wheel actually is. It's mass arranged in a circle, far from the center. When you spin it, every bit of that rim stores energy, and the energy it stores climbs with the square of how fast it turns. Engineers write it as 1/2 times the inertia times the speed squared. The important part for you and me is simple. Put weight out at the rim, get it spinning, and that wheel becomes a battery. Not an electric battery, a kinetic one. It holds motion the way a dam holds water, and it releases that motion into whatever you press against it. This is the flywheel effect, and it's one of the oldest pieces of practical engineering humans ever discovered. Potters used it 4,000 years ago. Their heavy stone wheels kept spinning smooth and steady long after their hands left the rim, and that stored motion is what let them shape perfect pots. Now here's why that matters for a tool. When you sharpen or cut on a stored energy wheel, you're not relying on a motor to constantly push. You're drawing from the reservoir of motion already loaded into the rim. Each pass pulls a little energy out, and because the wheel is heavy and the energy is huge, the speed barely drops. That gives you something no cheap powered tool can give you: consistency. A steady, unwavering cutting speed that doesn't surge, doesn't stall, doesn't spike the heat. My grinder's little motor lurches under load. It slows when you press and races when you let off, and that inconsistency is exactly what scorches an edge. The heavy wheel just rolls through everything at one calm, relentless pace. I tested this with a luggage scale and a bit of patience. I loaded a worn kitchen knife against my bicycle wheel and measured how much steel came off per minute compared to my powered grinder set to be gentle. The wheel removed metal at a rate that shocked me, and the blade never crossed 140 degrees Fahrenheit. Cool to the touch the whole time. My powered grinder, doing the same job, had the edge smoking at over 300 degrees within 30 seconds. Same task, wildly different result. And the tool that won was the one I built from garbage. So the clue is clicking now, isn't it? It's not speed that separates a great cutting tool from a bad one. It's stored energy delivered at a controlled surface speed. But that raised a bigger question that kept me up at night. If this is so simple, so cheap, so obviously better for sharpening, why did nobody sell me one? Why did every store push the screaming little high RPM machine instead? That's where I stopped tinkering and started digging, and what I found made me a little angry. Because this isn't new knowledge, this is old knowledge that got buried on purpose. The heavy flywheel grinder was the standard for centuries. Every serious workshop, every blade maker, every farm had a big treadle-driven grindstone, a massive wheel you pumped with your foot while you held the blade. They worked beautifully. They lasted 100 years. And that's exactly the problem if you're in the business of selling tools. A wheel that never wears out and never needs replacing is a terrible product. You sell it once and you never see that customer again. But a small motor spinning a small stone that burns edges and wears down and eventually fails, that you can sell forever. You can sell the machine, then the replacement stones, then the next machine when the motor dies. The economics rewarded the worst tool, so the better one quietly disappeared from the shelves, and a couple generations of us grew up thinking high RPM in a plastic housing was progress. The people who kept the real method alive were the ones who couldn't afford to be wrong. Craftsmen whose entire reputation lived or died on the edge of a blade, and nowhere did they refine it further than in Japan. Because here's the layer of the mystery I hadn't even reached yet. It's not just that the Japanese kept using the big wheel, it's how they used it, and what they figured out about the surface of that wheel that turned a good sharpening tool into something that borders on unfair. Let me show you what I mean, because this is the part that genuinely changed how I work. In Japanese blade tradition, sharpening was never one wheel and done. It was a progression, and the wheel was only the beginning of it. But the wheel itself carried a name and a method that goes back centuries. The foot-powered grindstone, turned by pumping a pedal while both your hands stay free to guide the blade, let a single craftsman control pressure, angle, and speed all at once with total precision. Both hands on the steel, no wobble, no slip. That freedom is why their edges became legendary. And here's the detail I want you to hold on to, because we're coming back to it as the final answer. It wasn't the hardness of the wheel that mattered most. It was something about the surface, something they controlled deliberately that let a soft, cheap grinding surface produce a sharper edge than a hard, expensive one. I'll give you the full secret at the end, and once you hear it, you'll be able to do it this weekend for nothing. That still amazes me every time I say it out loud, and if you want to go even deeper into the mechanics behind tools like these, I should mention something before we keep going. I've been putting the full framework, the physics, the forgotten methods, the practical builds into a series of books. Tool Mind, Steel Instinct, and Tool Master each take a different layer of this knowledge and lay it out so you can actually use it, not just watch it. If that's the kind of thing you want on your shelf, the details are in the description below. Worth a look before we finish this one. Now, some of you don't want a sharpening wheel at all. You want to know about that title, the wheels becoming serious tools, the real muscle work. So let me widen this out, because the same principle scales into jobs that have nothing to do with knives. Once you understand that a wheel is a stored energy machine, you start seeing uses everywhere. Farmers in Japan and across rural Asia turned wheels into treadle-powered water pumps, into rope-making machines, into threshing drums, into foot-powered lathes for shaping wood and metal. The bicycle, when it arrived in the countryside, became the single most repurposed machine in farming history, precisely because that wheel is a ready-made flywheel and gear system just waiting for a new job. A pedal-driven wheel geared to a small drum can power a grinding operation heavy enough to sharpen scythes and mattocks all day. The same setup with a different attachment becomes a winnowing fan, or a honey extractor, or a potter's wheel that runs smoother than any electric one because the mass keeps it dead steady. But first, I need to talk to you directly, because I know exactly what some of you are thinking right now. You're thinking this is fine for me because I found a decent wheel, but your bike wheel is bent, or rusted, or you don't even have one, and this whole thing must only work with some perfect wheel you don't own. This next part is built specifically for you, because the truth is the wheel almost doesn't matter, and I'm going to prove it with the sorriest scrap you can imagine. You do not need a true, straight, expensive wheel. A bent rim actually costs you almost nothing for sharpening work, because you're not spinning it at high speed where wobble matters. At the calm pace this method uses, a slightly warped wheel still delivers steady stored energy right where you press. I ran a badly dinged wheel that wobbled a full quarter-inch side to side, and the edges it produced were indistinguishable from the true wheel. So throw out the idea that you need something perfect. Here's how you build one from what's already on your bench. Take any old bicycle wheel, front or back, doesn't matter. Mount it so it can spin freely. The simplest way is to clamp the axle in a bench vise using the original axle nuts. And now you've got a wheel that spins on a stand for free. If the tire's still on it, strip it off down to the bare metal rim, or better, leave a strip of old inner tube around the rim as a backing. Now you need a working surface. This is where people overthink it and waste money. You do not need a special grinding wheel. Cut strips of ordinary aluminum oxide sandpaper, the same stuff in the little sanding drawer everyone has, and glue them around the rim with contact cement. Start with a coarse grit, around 120 for reshaping. Wrap a second wheel, or a second section, with a finer grit, around 600 or higher, for finishing. That's it. You've just built a variable grit precision grinding station for the price of a sheet of sandpaper. To drive it, you have two choices, and both cost nothing. The simplest is to spin the wheel by hand with one grip, while you guide the blade with the other, though that gives up the two-handed control that makes this method magic. The better way, the traditional way, is to rig a pedal. Take a loop of old rope or a strip of tire, wrap it once around the rim or the pedal crank if you left it on, and connect it to a board hinged at the floor that you pump with your foot. Now both your hands are free, exactly like the old foot-powered grindstones, and you steer the blade with total control while your leg does the work. I built mine in an afternoon out of a scrap 2x4, 2 hinges, and a length of clothesline. Total cost, if you had to buy any of it, under $5. And the beauty is the diameter is doing the heavy lifting for you. Because your wheel is so much bigger than any bench grinder stone, you get that low heat surface speed automatically. You cannot burn an edge on this thing even if you try, because you'll never crank a hand wheel fast enough to reach the temperature that ruins steel. The physics that protected my chisel protects yours. So the guy with nothing but a rusty bent wheel and a scrap of sandpaper ends up with a safer, cooler, more controllable sharpening tool than the guy who spent $300. That still amazes me every time I say it out loud. And that steadiness is worth more than it sounds. When I geared my wheel down and put a real load on it, I understood why the old craftsmen trusted these for the toughest jobs. The stored energy in that rim smooths out every hitch in your effort. You pump unevenly, but the wheel outputs evenly. Your muscles surge and rest, but the tool never notices, because the flywheel absorbs your inconsistency and releases smooth, constant power. No motor under $100 gives you that. The cheap ones cog and stutter. The wheel just flows. That's the difference between a tool that fights you and a tool that carries you, and it costs you nothing but the scrap in your shed. But I promised you the real secret, the buried core of this whole mystery, and it's time. Because everything I've told you so far, the surface speed, the stored energy, the low heat, all of that explains why the wheel matches or beats a powered grinder. It does not explain why the Japanese edges became the sharpest in the world. There's one more layer, and it's the one almost nobody in the West understands. And when it finally clicked for me, I actually said it out loud to an empty workshop. Here it is. The secret is not in the wheel's hardness, it's in the mud. Let me explain, because this sounds insane until you see it. In traditional Japanese sharpening, the finest edges never came from a hard, aggressive grinding surface. They came from a soft grinding surface that breaks down as you use it. When you sharpen on a natural Japanese waterstone, the surface constantly sheds tiny particles and mixes with water to form a fine slurry, a kind of grinding mud they call the abrasive paste, and that mud is the actual cutting agent. As you work, those loose particles roll and crush between the blade and the stone, and they keep breaking into smaller and smaller pieces. So the abrasive gets finer and finer with every single stroke, all by itself. You start with a coarse cut and finish with a polish, on the same surface, without changing a thing. The stone that wears away fastest gives you the finest edge, because its willingness to break down is exactly what refines the grit for you. That is the opposite of everything a hardware store tells you. They sell you the hardest wheel, the longest-lasting wheel, the one that resists wearing down. And that hard wheel, the one built to last forever and never shed, can never produce that self-refining mud. It just drags the same coarse scratch across your steel over and over. The expensive, durable surface is fundamentally worse at making an edge sharp, and the cheap, self-sacrificing surface is better. And now you know the reason nobody wanted to sell you the good one. A tool that consumes a little of itself every time you use it means you buy grit again. A tool that lasts forever. They can only sell once. The economics buried the better method a second time, at the level of the surface itself. So here's how you put that final secret onto your scrap wheel this weekend, and this is the part that turns your bicycle wheel from good into genuinely unfair. Instead of only using hard sandpaper, dress the rim with a soft, self-breaking abrasive. The simplest version, the one I use, is to make a slurry. Take a bar of inexpensive abrasive, a chunk of pumice, or even a piece of soft sharpening stone, and rub it against your wet wheel to load the surface with loose grinding paste. As you sharpen, keep the wheel wet. Drip water on it constantly. That water carries the loosened particles into a mud, and that mud does the same self-refining magic the old masters relied on. Your coarse start becomes a fine finish on one wheel, kept cool by the water, driven by the stored energy in the rim, at a surface speed that can never burn your steel. Every principle we uncovered stacks into one motion. That is the whole solved mystery, sitting on a stand you built from trash. I want you to sit with how complete that is. The heat problem, solved by the big diameter and the water. The power problem, solved by the flywheel mass. The consistency problem, solved by the stored rotational energy. And the sharpness problem, the one that separates a working edge from a razor, solved by the soft, self-shedding mud that the tool industry spent a century training you to avoid. 4 problems, 1 wheel, $0. Bladesmiths worked this out generations before any of us were born, kept it alive by hand because their livelihood depended on the truth instead of the sales pitch, and it survived just long enough for you and me to dig it back up. I keep thinking about my old farmer friend and his 40 years of blades sharpened on a junk wheel, and how I nodded at him like he was a relic. He wasn't behind the times. He was holding a piece of knowledge that the times tried to erase. The first blade I finished with the full method, water and mud and stored motion all working together. I shaved the hair off my forearm with a kitchen knife I'd nearly thrown away. That knife had been dull for years. My expensive grinder never once brought it back. A wheel from the dump and a handful of mud did it in under 10 minutes, cold to the touch the entire time. So let me hand you the whole thing in one breath. Speed was never the answer. A big wheel moving slowly beats a small wheel screaming because surface speed cuts and heat destroys. Mass is a battery. Load it up and it pours smooth power into your work no cheap motor can match. And the surface should sacrifice itself, break down into mud, refine its own grit, because the tool that wears is the tool that sharpens. Everything the aisle sold you was the opposite of every one of those truths, and now you can see exactly why, and exactly how to build your way out of it for the cost of a sheet of sandpaper. You didn't lose anything by not knowing this before today. You just got it back, and it turns out it was leaning against your shed the whole time, waiting for you to stop seeing junk and start seeing a machine the old masters would have recognized in a heartbeat. That's the whole thing about people like you and me. We'd rather crack the puzzle and build the answer than hand over $300 to be told what to think. We take the thing apart. We find out why. We keep the knowledge the sellers hoped we'd forget. So do me a favor and tell me one thing down in the comments. When you build your wheel, are you going the hand crank route? Or are you rigging the foot pedal like the old grindstones so both your hands stay on the blade? I really want to know which way you go, so drop it below, and tell me where in the world you're building yours, because I read every one of these. If you're the kind of person who'd rather understand a tool than be sold one, who takes things apart and refuses to be fooled twice, then you already belong with the rest of us doing exactly that here. Stick around, because next time I'm taking an ordinary steel shovel, the flat kind rusting in every garage, and turning it into a cutting tool that slices through roots and packed clay like they aren't even there, using one bend the factory hoped you'd never think to make. You're going to want to see where that one bend goes. So that's the idea behind it, but we just scratched the surface. Inside the Workshop Guild, I walk you through the full bicycle wheel sharpening station build, right where this video left off. And if you get stuck, you can ask me directly, and I answer you myself. No robots. You won't be tinkering alone either. Just point your phone's camera at the code on the screen, and you can cancel any time with one click.